presenter is Xiang Yi from Google.
Presenting team. So how can I present the slide? Okay.
I take the opportunity for just introducing this paper. This paper presents a novel approach to address the challenges of online learning on large-scale recommender systems with large action spaces. So the authors propose several techniques to enhance the efficiency of updates and exploration while leveraging clustering and embedding methods. All the authors are from Google.
Don't know how to make it work.
Okay, where is your presentation?
Oh, so it's in the folder.
This is not your presentation.
This is not mine yet. Yeah, I don't know why it's open. So. Yeah, I will mention this one.
This one, right?
Yeah, yeah. Okay, yeah, thank you. Hello, everyone. Sorry about the small delay. So my name is Xin Yang. So I work at the Google DeepMind. So actually, Xiaochuan standing beside me is joining me today for this talk. So we are very excited to introduce online matching, which is a real-time Bandit system for large-scale recommendations. So this is joint work of many of my great collaborators, not just Xiaochuan, but also Raining, Harry, Charles, Lukash, Li Chen, Miming, and Ed. So in the beginning, I want to start with some motivations about why we initiated this project at Google. So first of all, we know that batch machine learning powered by neural models has been a great success for industry scale recommendation system in the last 1 decade. By batch ML, I mean that we typically leverage large amount of logged user feedback to train our neural models. And we push this model to serve live traffic version by version in the batch manner. So although this is a great success and standard practice for industry, but we realize there are still a few critical challenges. So the first one is very obvious. So we have this kind of feedback loop from existing recommendation policy. What I mean by that, the data we use for training our neural models is influenced by the existing recommendation policy. So this will cause the, basically, this will lead to the problem of reinforcing existing data bias in the training data, cause the rich gets richer problem or the information bubble problems, which prevent users to explore new interests. They might be new topics they might be interested in. And in the same time, we observe a long delay from user feedback to model update. So the latency can be a few hours or even a few days. So this is not ideal for applications with dramatic distribution shift, particularly if you are building an application where a huge amount of new content is created very frequently. And fundamentally, I think the problem is that supervised learning is not designed for exploration. So it aims to pick the best actions from observed data. However, it does not explicitly encourage exploration of new actions. So for all these challenges, we know that online learning is a pretty promising framework. However, when it comes to designing industry-scale online learning systems, we see a few practical constraints. So the first one is pretty obvious. So we have a very large exploration space. So we are talking about maybe recommending and exploring millions of fresh videos per day or fresh items per day. And in the same time, we have very limited exploration traffic. So the problem is that exploration usually comes with a negative user impact. So we need to be really careful about making the trade-off between exploration and exploitation. So finally, I want to call a lot of mature machine learning platforms are designed and built for batch ML. So for online learning, there could be simply engineering challenges about how to designing and build a system that can scale up to huge real-world user traffic while maintaining a small latency at the same time. So our work actually aims to address these practical concerns. So this is sort of the agenda for the rest of this talk. So we'll basically first introduce a novel framework for building real-time Bandit system. So we call this offline plus online hybrid approach because on very high level, we first use batch machine learning to reduce the exploration space for online learning, and then we use online learning to build this kind of closed-loop system that can directly interact with the users. In order to scale this system to serve real-world applications like YouTube recommendation, we will further introduce algorithmic extension of the NUC algorithm. So we'll show how this system will work with real-time traffic and millions of videos in YouTube. And finally, Shaochuan will talk about 2 experiment frameworks for fresh content discovery and corpus exploration. So we'll basically show how useful online matching is for these 2 applications. So let me first provide you some intuition about how we approached our framework. So we can take a very simplified view of the recommendation problem. So as I show in this diagram, recommendation is nothing but a matching problem between user and items in this dense bipartite graph. So our job as machine learning recommendation researcher and engineer is to figure out what are the valuable edges from this graph. So, but this view is not suitable for online learning simply because there are so many edges in this graph, and it's very hard to design efficient algorithm to explore all these possibilities. So our insight is actually very simple. So we try to sparsify this graph to make it flexible and tractable. The way we do that is that we first rely on offline learning to train this kind of dual encoder, or you can also call it two-tower models, to co-embed the user and item into the same embedding space. And then we can start to sparsify this graph. So first of all, we will take a bunch of offline user embeddings to build the user clusters. And for each cluster, we'll have the central embedding. And then we connect each cluster to a few top K items on the right-hand side by using the similarity between the central embeddings and also the item embeddings. And then for each user request, of course, we don't want to assign every user to a single cluster. So we assign it to a few top K clusters as this kind of context representation. As you can see, the cluster assignment is determined by neural models. So that's learned offline. And the sparse edges in this sparse bipartite graph correspond to the Bandit parameters, which we want to learn online through live traffic. So now the question is that how can we optimize those Bandit parameters? How can we learn those Bandit parameters in the principal way? So it turns out we can model this setup as a sparse linear contextual Bandit problem. The idea is that we can basically treat every cluster as one coordinate in the high dimensional space. And then you can see that for context vector W, because we only assign every user request to a few top K clusters, so in the high dimensional space, W vector is actually very sparse. And also because of how we constructed the graph by restricting, say, top K items per cluster, we can see the parameter for each action or item, I will use these 2 terms interchangeably, the parameter for each action is most likely to be sparse. So this means that both context vector and parameter vector, they are sparse. So if there are no support overlap between these 2 vectors, we simply assume the reward is 0. So basically, we will not explore this kind of user request and item pairs in live traffic. So with this view, we can start to think about how to use the classic LinUCB algorithm for solving this problem. So I think this is promising, but in practice, we also realize LinUCB has some limitations. So first of all, it needs to maintain a large covariance matrix per action. So, and it also needs to compute the inversion of this matrix whenever you want to compute the upper confidence bound. So this is definitely not scalable. So our idea is also very simple. So we propose to just use the diagonal terms of the covariance matrix. So in this way, you can see that there is no more matrix inversion. So computing the upper confidence bound is super lightweight. And in the same time, more importantly, we no longer need to kind of do the strictly synchronized update on the item level. We can basically distribute the bandit parameters across all the edges in this sparse bipartite graph. So it turns out this approximation significantly improved the throughput we can support. So now I'm going to hand you to Shaochuan for the system and experiments.
Thanks, Xinyang. At high level, this slide shows the pipeline as a hybrid approach. On the bottom of the diagram, you can see we leverage the two-tower model and the offline training processes that Xinyang previously mentioned and specify the graph. So we build a bipartite graph offline, and this graph is going to be exported periodically to the serving layer. Once it reaches the serving layers, the online agents, which is the Bandit algorithm Xinyang previously presents, happening in this real-time feedback loop, whereas the agent is taking the feedback from the users and react accordingly through these explored items. And if we zoom in, the real-time feedback loop of the upper the diagram, you will see this closed feedback loop where the user feedback are aggregated and into per cluster and video pair into distributed storage like big table. And this, what we call bandit parameter, which is are collected collectively from across all the users and their clusters. And these bandit parameters will be joined with the vocabulary generation, what we call the bipartite graph generations, into the candidate lookup service tables. And on the right-hand side, this is a table that we illustrate how you could potentially schematize the data to be stored. And I want to highlight one thing about this is that you can see this is a co-design with assistants and the algorithm to support high QPS as well as high updates. Yeah, so if we look at the system performance, there are two types of latencies here. The first one being policy update latencies. What I mean by policy updates means that once a feedback is provided by the users, how long does it take from the feedback happening to the point that the agent is able to see that and react accordingly. And second latency is what we call corpus latency, update latency, is where a video get eligible to be exploration. How long does it take to enter this exploration pool so that agent is able to explore them? And we found that the policy update latency is actually quite critical in terms of the exploration efficiency and the performance as we introduce the artificial latency delay in this feedback loop. The agent will incur more regrets as if the feedback is not delivered fast enough. That, as you can see, if we introduce 20 minutes more, you will see more CTR drops on the explore items, and then it's, in addition to 40 minutes delay, the CTR even drop more. And then we deployed the proposed system to two applications. The first being the fresh content discovery. And the goal here, the business goal here is trying to identify the superstars tomorrows. And for this, we leverage, use a explore and amplify strategies to allocate a small percentage of the traffic and then to explore these small percentage of user to this exploration experience, and then we collect the bandit parameters through this small percentage of the users, and then amplify to all the users for the winners. So through this, we observe some positive impacts on the user engagement on the exploitations. And by exploitation, I meant that in a UCB or diagonal UCB algorithm, there is a parameter called alpha, which is tuned the exploration turns during exportation, we just shut down the exploration turns so that it's fully exploited. And the second applications that we deployed is basically we would like to enlarge, or you can say co-star a lot of tail creators or tail contents where we would like to expand the recommendable corpus. The reason being this is traditional recommendation system usually reinforce the existing winner in the corpus, and we will ideally we would like to hope to be able to flatten this curve without hurting the users too much. And then the challenge here is that usually if you do this, you will incur short-term engagement loss, and then online matching is actually pretty well suited to solve mitigate this issue by this real-time feedback loop that the agents that be able to see from the explore items. And to measure this impact for a user and a corpus, we leverage this setup we call a viewer corpus correlated experiment setup, so that we divide the entire corpus into several chunks and then co-divert the user traffic to the actual corpus. In this way, you are able to measure the cohort of the different corpus to understand how exploration is effectively affect that specific corpus, and at the same time able to understand how it's impacting the user and be able to measure both the cost of exploration as well as the expanded corpus measurement on the right-hand side. And as you can see, it's much, we increased that recommended corpus by about 5 to 7%, depending on the thresholds that you're counting. Yeah, with that, I'm handing over back to Xinyang to talk about some takeaways.
Yeah, thanks, Xiaochuan. Just some quick takeaways. So in this work, we introduced online matching, which is highly scalable real-time bandit system for large-scale applications. So we talk about some of the key insights about how we approach the final framework and how we make this problem feasible and tractable through some engineering, basically system and algorithm co-design. And finally, Xiaochuan have talked about some experiment results about the two important applications, how we can quickly discover the high-quality fresh content and surface them to our users, and we see this kind of nice daily active user improvements. So this is basically shows the benefit of surfacing high-quality fresh content to our users, and also increasing recommendation corpus size. This is also very critical. So we have been showing that online matching is a very promising framework for this application. So because we are standing between you and launch, so maybe some food thoughts. We realized that there are some open questions from our work. So the first one is that we are basically considering this kind of explore and amplify strategy for fresh content discovery. So we run two parallel slots together. So this is in contrast with the classic Bandit setup where we basically care about the user regret in a single slot. However, in here, we care mostly about the improvement from the exploitation slot. So how we can design better algorithm, maybe principal algorithm for this setup. So this remains very interesting. And secondly, I think compared to the classic multi-arm bandits framework, our arms here are actually very dynamic and changing rapidly from time to time because we keep exploring new items uploaded to our platform. So how can we design principal algorithm in this setup? So I think that's another interesting direction that we can all think about. So I want to put a very quick ad here. So our team, Google DeepMind is hiring. So we have multiple exciting projects in the direction of personalization, user modeling, sequential recommendation, as well as recommendation retrieval. Online matching is one of the exciting examples. And also, more recently, we are actively exploring the interaction between LLMs and the recommendation system, which is actually a trending hot topic. So if you happen to be interested in any of them, feel free to drop me a note. So with that, we'll end my talk, so we can probably take some questions. Thank you.
Thank you very much for your really interesting presentation. Questions?
Yeah.
Please.
I got one question. One general question. I know that Bandit-based systems are widely used in industry, but I don't know why they are used. Could you elaborate more about this, their advantages as compared with non-Bandit-based systems?
Yeah, I think this is a great question. So basically, in the beginning, I showed that there are some limitations about kind of the supervised learning system. So we have the kind of exploration problem, right? So because we basically reinforce the data bias from our offline data. So in order to explore maybe long-tail items or explore the topics user has never engaged with but potentially be interested in, there are some fundamental limitations of those kind of the standard supervised learning approach. So that's why I think Bandit is a very promising technique, because it provides the very principal framework for you to consider about the data uncertainty and try to proactively connect the data by interacting with the users. So I think, yeah, that's my understanding. Anything you want to add? Okay.
Thank you.
Okay, please, Robin.
So the you're clustering the users, you're associating a particular number of items with those clusters. Probably you're not reaching all the items, right? So it's not, you're not really exploring all the space of the items. So I'm wondering how sensitive are your results to the choice of K and the amount of the item space that you explore?
Yeah, I think this is a great question. So I think in terms of how many items, how deep corpus we can explore, I think it depends on how much traffic we can have for exploration and how much short-term negative impact we can tolerate. So I think those are pretty important to consider. I think in one of our table we show that compared to the baseline, we double the graph size by including more candidates into the graph. We actually see improvement from the fresh content discovery experiment. But in the same time, we realize we have to double the exploration traffic. So I think definitely if you have enough traffic, you can definitely explore more. But yeah, be careful about the exploration cost and also the overall user impact.
Okay, left side for fairness.
Thank you for your great talk, for the insight that you shared with us. I have a question about the algorithm you use for the exploration, so LinUCB. LinUCB is a great algorithm that has regret guaranteed, but the way in which it explores, since it's always select the arm which has the largest upper confidence bound, sometimes if there is some issue like you can't update the parameters, it means that you will explore less efficiently, and sometimes it can happen in production. So my question would be, have you considered also other algorithms or tested other algorithms that doesn't suffer with this problem?
Yeah, I think in our system we also support Thompson sampling. But I think one problem is that when you assign every user to multiple clusters, how can you incorporate the cluster weights into the Thompson sampling? So that's something we thought about but haven't figured out. I think, in our system we actually do some approximation, do some variant about the LinUCB, because we still have the latency, right, from the user feedback to when the system can incorporate that feedback into Bandit parameters. So because of that small latency, we actually do top K randomization. So not just pick the item that has the highest upper confidence bound. So we pick a set of items that has the highest confidence bound, and we do top K randomization just to, because we have this kind of small latency. Yeah. We do consider other algorithms, but so far we still think LinUCB, because it provides the very nice framework for modeling the context vectors, so it fits very well into the sparse graph view of our paper.
Okay.
Thank you.
Please. Okay. The last question.
Thank you for the great talk. I want to ask you about your two-tower model that used in clustering graph construction. What are crucial features helped you to get the right distribution for this graph construction? Looks like there is a lot of buckets, 30K. What are features?
Features, actually, in my slide, I linked a paper we published 4 years ago at RecSys. So the model architecture is almost, this is very similar to that version we published. I think we consider a lot of user features, especially user sequence features, and also context features of the video user is currently watching, and a lot of content feature about the candidate videos. So yeah, I think, yeah, so those are pretty like, yeah, I think we have those details in our previous paper, maybe you can check out. But I think you raised one good question about, shall we do something specific to the offline modeling to better align it, basically align it better to online exploration? I think we haven't done anything specific to that, but I think that's sounds a very interesting direction to consider about.
Thank you.
Thank you.
Can I ask one more question?
One more question, please.
Hi. Thank you for the great presentation. I wanted to ask one thing. Is when you're creating the graph, right, is it done incrementally or you are doing it from scratch after each batch?
Oh, this is a great question. We actually do that incrementally. So at every point, we take a snapshot of the most recently uploaded item to the system, and we create an incremental version of this graph, and we merge that to the previous version of this graph, so to create this kind of combined graph. Yeah, but for some previous snapshots, we will also expire those versions. So we have a moving time window sort of to capture, yeah, what's the time window of the content we want to explore. Yeah, great question.
And also, does the number of clusters remain the same or with each iteration or it changes?
We do retrain the cluster central embeddings, but we won't start from the previous version. So we do allow small distribution shift, but not too much, because otherwise the different cluster versions won't align with each other. So yeah.
Thanks a lot.
Last question, because the time is over, please.
Hi, question about evaluation. How do you evaluate your system online, especially how do you exclude, separate the exploration effect for your users and the content? Because when you do the exploration, it will pollute your control group too, right?
You are talking about the corpus exploration, right? So
yeah.
Yeah, so that's why we are not using the standard A/B testing by just like diverting the user traffic. We also divert the corpus. So that's why we call it a user corpus co-divert experiment in order to measure the counterfactual impact on the corpus size. So yeah, does that answer your question?
Okay, thanks so much
Yeah.
to all the presenters and the audience. Now the session is over. There is the lunch break, and there is also the poster session. You can discuss with the poster authors about their very interesting work. And the second session will start at 2 p.m. See you later.